We'll now define our central limit theorem. And the central limit theorem is specifically concerned with the sampling distributions of means, like we did in the last video. In particular, what it says about this is that the mean of these sample means is equal to the entire population mean. And the standard deviation of the sample means is our standard deviation divided by the square root of our sample size. What this means is our z-value is going to change slightly to be x bar minus mu over sigma over the square root of n. And this is going to all hold under two conditions. One, either your variable is normally distributed ahead of time, or two, if that's not true, you have a sample size of greater than or equal to 30. So what the central limit theorem now lets us do is, before, when we were looking at the probabilities and the areas under the curve, we were looking at a single person. What is the chance that a single person will satisfy our condition? And this now allows us to look at a group of people rather than a single person. Let's do some examples to help explain this a little more. We know that IQ is normally distributed and it has a mean of 100 and a standard deviation of 15. I want to know what is the probability that someone's IQ is less than 120. And this is exactly what we were doing before with normal distributions. We need to find our z-score, so we have our data value minus the mean divided by the standard deviation, which ends up being 1.33, and then we need to look this value up in the z-table. We'll then move to our z-table, look for 1.3 down, and then over to the next 3 to get 0.9082. So this probability, 0.9082, since we were looking at the probability that this was a less than, we do have that it's shaded to the left, so this is our probability. This is exactly what we've been doing. So how does the central limit theorem change things? This time, I want to know what the probability that the average IQ of 4 people is less than 120. So I'm no longer dealing with a single person. Instead, I'm dealing with, in this case, a group of 4. So now my z-score is going to change. I still have the data value minus the mean, but this time I'm going to divide by the square root of the sample size, which is 4. This gives us a z-score of 2.67 that we now need to look up in our table. We go down to 2.6 and then over to 7 to see our probability is 0.9962. So back at our example, we now have a probability of 0.9962, which is greater. So the chance that one person has an IQ less than 120 is actually going to be smaller than the chance that out of 4 people, the average IQ is less than 120. Let's look at another example. This time, let's consider we're at a restaurant, and we know the average wait time is 15 minutes with a standard deviation of 2.5 minutes. For 45 randomly selected people, what's the chance that the average wait time is going to be more than 14 minutes? Well, we have our value that we're looking at, 14, minus the mean divided by the standard deviation over the square root of the sample size. And while we haven't said this is normally distributed, we do have a n, 45, greater than 30, so we can use this. If we work this out, we get negative 2.68, so we need to look that up on our table. Here's our table. We'll go down to negative 2.6 and then all the way over to 8 to get 0.0037. Back at our problem, we had gotten 0.0037, but that always tells us the area to the left. And we want to know what's the chance they waited more than 14 minutes. So 1 minus 0.0037, which gives us 0.9963.